Hi children, today we are going to continue our fifth chapter, that is periodic classification of elements. Before moving to the topic, let me give you a quick revision. This chapter do have two parts, that is one is history of periodic table and second one is trends in periodic table. In history of periodic table, we have already discussed classification of Lavoisier, Dauberenius triad, Newland's octave, Mendeleev's periodic table, and modern periodic table. And the second topic is trends in periodic table. We are going to discuss what are the trends in valency, atomic radius, electropositivity, electronegativity, and metallic and non-metallic nature. Okay, so as we have already said, valency, these are the topics we are going to discuss. First of all, we are going to discuss what is the periodic trend in atomic radius or atomic size. Okay, here we are. Atomic size and atomic radius. So what is atomic radius? That is a very basic question. Atomic radius. From the picture itself, it is clear that it is a distance from the nucleus to the outermost shell of an atom, and that outermost shell should have an electron. So what is atomic size? Sorry, atomic radius. It is the distance between the nucleus, center of the nucleus, to the outermost shell which is having the electron, and that is also considered as atomic size. And in order to measure it, we already know that in order to measure the what length, we have meter. We can take meter as a unit, but since this size is so small, so tiny, we will take picometer or picometer. And what is the conversion of 1 picometer into the meter? That is 10 raised to minus 12. And we know that the smallest atom is hydrogen, and the size of atomic radius of hydrogen is 37 picometer. Okay, so from the picture itself, it is clear that how to calculate the atomic radius. I hope it is clear. So our concern is what happens to the atomic radius if you move from top to the bottom or left to right in periodic table. Here we are. Okay, down the group of top to bottom, what happens to the atomic radius? In order to understand that trend, let me give you the electronic configuration of alkali metals. So what was alkali metal? Can you remember what is alkali metal? Alkali metal is the name of first group elements. Okay, which are the first group elements? Lithium, sodium, potassium, rubidium, cesium, and francium. I hope you remember all those things. Okay, here we have given with electronic configuration of lithium, sodium, and potassium. What is electronic configuration of lithium? 2 1. It is having two shells. In sodium we have three shells, that is 2 8 1, and in potassium we have four shells, that is 2 8 8 1. So here we are given with Bohr model of these elements. Lithium, Bohr model of lithium is there, Bohr model of sodium, and Bohr model of potassium. From the picture itself, it is clear that when you move from top to the bottom, the size of atoms are getting increased. Why the size of atoms are getting increased? Because the number of shells are getting added. So my question is, what happens to the size of atom, radius of atom, when you move from top to the bottom in group? Atomic size increases. Down the group, atomic size increases. So what is the reason for that? When you move from top to the bottom in a group, a number of shells are getting added. That means, that indicates atomic sizes increases. So what happens? Next question is, what happens to the atomic radius when you move from left to the right, or along the period? What is the change? Here we are. Along the period, or from left to right, what happens to the atomic size? Okay, in order to understand that, here we are given with the elements of second period. So which are the second period elements? Lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine, and neon is also there. So but for certain reasons, we have omitted neon from here. Okay, so electronic configurations are given there. Lithium 2 1, beryllium 2 2, boron 2 3, carbon 2 4, nitrogen 2 5, oxygen 2 6, fluorine 2 7. Okay, if you draw the Bohr model of these atoms, you can see the its picture is given here. Bohr model of lithium, Bohr model of beryllium, boron, carbon, nitrogen, oxygen, fluorine. Listen, first thing, listen, number of shells are not adding or increasing here. Number of shells are same. How many shells are there in lithium? 2. How many shells are there in beryllium? 2. In boron, shells number of shells are same. 2. Carbon 2, nitrogen 2, oxygen 2, fluorine 2. So first we will think that there will not be any increasing atomic size. The atomic size will be same, but atomic size are getting decreased. So it's an interesting fact, right? Why the atomic size are getting decreased? Look at the size of lithium. Lithium do have 2 shells and 3 protons. How you got the number of protons in lithium? Because atomic number, listen to the atomic number of lithium, it is 3. So number of protons in lithium is 3, but number of shells are 2. Number of protons in beryllium is 4, but number of shells are 2. Number of protons in boron is 5. Number of shells are same. So one thing is clear, if you move from left to right, number of protons are increasing. That means nuclear charge is increasing. But at the same time, when you move from left to right, number of protons are increasing, but number of shells are same. So these protons can attract the outermost shell, and if you move from left to right, number of protons are increasing. That means nuclear charge is increasing, so their attractive power will be increasing. So what happens? The attractive power of nucleus increases, atomic size getting decreased. That is a very thing happened here. Along the period, the size of atom is decreasing. Why? The reason is given here. Moving from left to right, number of shells remain same as we already discussed, but nuclear charge, what is nuclear charge here? Ability of nucleus to attract the outermost electron is getting increased. When the nuclear charge increases, nucleus will attract the shells closely. That means atomic size decreases. You have to keep one thing in your mind, that moving from left to right, nuclear charges increases because number of protons are increasing. Okay, next, so nutshell, we can see that, so from the picture itself it is clear that when you move from left to right, atomic size decreases. It is given here, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, size is getting decreased. Okay, the same pattern is followed in third period, fourth period, fifth period, sixth period, in each periods. Okay, and what is the case in the atomic size when you move from top to the bottom, down the group? It is crystal clear. It is given there, right? Lithium, sodium, potassium, rubidium, cesium, the size is getting increased. So I hope what happens to the atomic size, or what is a trend in atomic size in periodic table, is clear. We will move to the next topic, that